So we haven't gotten completely through the process, but here I basically did a quick overview of what we have so far. Um, Basically, the example was clearly documented, as everyone has said. It's been very easy to follow. You guys did a fantastic job, especially with segments. I think it's easy enough for people who aren't too familiar with coding to be able to go in there and even just copy and paste the lines that you provided and modify the certain sections that you need. So we were able to get through it without any issues, and yeah, it's very, very well done. As far as our own model, it's up on GitHub and exploitable. As far as with Docker, I believe it works, but as was just mentioned, I haven't been able, due to the number of inputs, I haven't been able to or know if it's possible to try executing it from the Docker image in order to make sure that everything is kind of a quality assurance check. So that would be something I'd like to talk to you guys about and how to go about that, or whether it just has to be in the VLab. And that we can't just execute the model solely without the inputs, because the way it works is it just will fail if it doesn't have all the required files. And then a lot of comments about inputs and enabling in the VLab, but I'll get to those later. So briefly, we're using the Delph 3D model. It's actually a collection of models here, where it's Delph 3D flow morphodynamics, which is a sediment transport model and erosion model, wave, which couples with the flow model, water quality, an ecological component, which is an added-on model of bloom, and a particle tracking module, which is able to do oil spill detection and modeling. And thankfully, with the help from some colleagues, we were able to kind of get the potential for the entire suite to be executed. But we're just going to be focusing on getting the VLab. So the GitHub exposes the entire modeling suite, but we're just focusing on getting the one water quality component to be functioning with the VLab. So briefly overview, it does several different processes. The water quality actually does recalculation of suspended sediments, as well as dynamic growth for phytoplankton and an entire array of alga. There are over 23 different types of alga within the model, as well as tracking the spread and concentrations of various nutrients like silicates, nitrogen, phosphates, and dissolved organic carbon. This is done through a collection of advection and dispersion equations. I won't show all the technical background. It's all listed within the GitHub account in the documentation for those who are interested. Also, through the coupling of the sediment transport model, it's able to do deposition of organic carbon and nutrients, which get deposited into the sediments. And also within the sediments, there are dynamic processes such as benthic grazers and microphytobenthos or other benthic alga, which can uptake deposited nutrients as well as access them from the water. Additionally in this, the pore and sediment water quality is monitored, and all these elements are put into outputs in large map files, which are the dynamic output source, which can be accessed through a variety of tools, which are also provided. But here you can see basically these are all a short version of the different processes which are calculated. There's also atmospheric deposition of various elements. So one of the additional required element is all the atmospheric conditions and concentrations of things such as carbon or nutrients, which are deposited into the model. So it's a fairly complex model, which requires many, many inputs. For the actual execution, there are different numerical solvers, including finite elements and many others. Within the program itself, you can select the numerical solver which best fits your needs. We found that due to the ability to create your own dynamic grid, when the gridding becomes so small, the resolution of the grids are so small, some of the more rapid numerical solvers fail due to basically their inability to calculate the fluxes at the interface of grid cells. So there's many options. Again, these are one of the customizable inputs into the model, which need to be selected. All the math, I won't bother you with the equations, but they're all in the various manuals which are openly available and also cited to on the exposed GitHub version of the model. It's mostly written in Fortran, but it is wrapped in a way so that interfacing with the model structure can be done through either a GUI, or in the case in which we're exposing it, the GUI will be built onto the VLab, but all the background coding and the inputs are done through text files, and it's executed through a shell script. So it's all wrapped up nicely. Again, the growth algorithms, specifically for this because it's the water quality, we have multiple algal species and functional types. And also the benthic organisms have now become dynamic, so there is dynamic recruitment, and using the particle tracking component of it, they're able to essentially spawn and move and repopulate and grow over an entire area of interest. And here you can see at the bottom just a quick overview of what's required to get ecological process, which is the water quality portion of it, running. It requires the inputs from the hydrodynamic model, the sediment dynamic model, or you can have a sigma forcing function, but it does require sediment dynamic inputs for all grid cells, as well as calculated or assumed riverine discharges along with nutrient loads as a portion of volume. So basically a concentration which is applied to the entire volume that you're putting into the system. And the meteorological forcing is also carried through the hydrodynamic and needs to be coupled onto there. So as far as inputs, there's a fairly high demand for the model. And then what you get out of this is primary, secondary production, as well as all the indicators such as the light attenuation coefficient, salinity, nutrient concentrations, chlorophyll concentrations, benthic biomass, and the list goes on. So with the system, what we found to be one of the most interesting aspects is to allow people to change their grids. So there's dynamic gridding, both structured and unstructured at different resolutions. And as you can see the difference in these two, there's a clear reason why you would need different numerical solvers to be able to resolve this situation. And then this is a look at the outputs. With the viewers we have, you select essentially your, you can select your element of interest, be it salinity or chlorophyll A, and it's displayed in a 3D environment. So you can click on any of the cells and basically explore what are the concentrations and time series within them. So that's a brief overview of the model. For GitHub exploitation, we have it up on the GitHub. All the different components are in there. The one catch is for us, the way we could do this was the download of the code actually still comes from the Deltatis central repository. So it requires a sign-in credential from the Deltatis website, which is a free account. Basically, you have to provide your email, but it shouldn't be an issue. And we've provided a link to this on the GitHub, so people can also do this quite easily if they're trying to set this up within the access this via the virtual lab. This will provide a copy of all module codes. We've also provided within the GitHub step-by-step instructions. So if there's any issues or questions, this can all be resolved via the information put on here. One of the limitations is that it does require to be run on a Linux host. So CentOS, Ubuntu, Butcher Docker, it does require execution on Linux. So that's currently the way that this source code has been provided. It's the way that we, well, at least I normally run the code. So that's the way that I've provided it. And then we've also provided how all the step-by-step, similar to, we followed basically your outline via your instructions on making sure it's very clear if someone needs to access any of this. For Docker, again, like someone also mentioned, the Docker toolbar it's not as handy. So it's a little bit inconvenient for those of us not on Windows 10, but I believe it works. It seemed to have worked, we'll put it that way. It was a little, yeah, I was a little bit confused as to what was all required within Docker, but I think it's worked out all right. And then, as was mentioned by, I'm sorry, I forget, as was already mentioned though, it would be great to know if there's a way to do test executions within Docker, simply because I mean, I believe that it works well and that it can be executed, but being able to actually test it would be great. And I'm not sure if there's an easy way, or yeah, you folks already know a way of doing that. So that's one of the questions that I've had. Sorry. And then for the Docker application, this is where this is basically the point that we're at, the Docker application within the VLab. The listing of the inputs, and basically I was going through all the formatting here. One of my major questions was, I'm not sure in other people's models, but in ours, there are many input files. If I list them singularly, over 100 input either parameters or variables which need to be listed. For us, we normally have a selection of about 10 to 12 actual input files, which within those, we list all of the other required elements. But one of the issues with those is for the sourcing of inputs, say for this example, you need the hydrodynamics and water quality and the hydrodynamics and the sedimentation processes. Those need to be, the source files for those need to be read in from an input file. So the model cannot execute without having a predefined directory to access these from. So these are the more technical questions though. So everything was pretty clear up until how to get, manage and store and access all of the inputs. And also one of the issues I saw was with the outputs. This model produces a massive amount of data with when executing the calculations. So at each of the time steps, it's creating lots of temporary output files, and I'm not sure whether these need to be listed within the VLab as well, because if they're not, then they won't be recognized or registered. So input-output section is where we've basically run into a blockage and need to have a little bit of discussion with you. But otherwise, everything's been going quite well, and yeah, well, once you get going with it, it's really not that bad. And I think that's yeah.
Thank you very much, Alex.